Hi, welcome to Introduction to the Imaging Sciences. This is going to be chapter one of your physics course for Rad Tech, and I'm going to focus mainly on the highlights to avoid this video being too long. All right, so first up, we have some quantities of or units of measure. It's important to distinguish that fundamental quantities are the basics, at the very bottom of that pyramid. So mass is in kilograms usually, length in meters, m there, and time is in seconds. We deal a lot with seconds in radiology because it could be seconds that we are setting on the control console. But what's important to remember is that these units of measure here are often used in derived quantities. Derived quantities involve a formula, not just a measurement, but a formula where several different things are used, fundamental quantities and figuring things out. I put this video here to help you remember derived and drive, right? So when we're driving, we accelerate. Maybe we're driving to the city, we have velocity. The car has momentum. Maybe we're driving to work, and drive sounds like derived. So remember, derived quantities, they often involve motion or kind of doing something. So again, maybe we're driving to the city, and velocity is measured in meters per second. If we want to figure out acceleration, we not only need to know the velocity when we get somewhere, but also what velocity we started at over the amount of time it took to get somewhere, that will figure out acceleration. One thing I do want to note about these different formulas that you'll see is that when you see an italicized M, so it's kind of like has that slant on it, that's going to stand for mass. So you have to be using, mass, maybe kilograms, things like that. When you don't see it italicized, it stands for meters. All right, up next, Newton's first law. This might seem kind of odd to be talking about in radiologic technology, but it's used because an object at rest, it tends to stay at rest, right? And an object in motion stays in motion. If we didn't have things like friction or touch, that sort of a thing, atoms in the air, things like that, things would either never move without a force being applied or move forever, like out in space, right? If we think about those movies where an astronaut gets released from the spaceship and they will just float forever, right? But on Earth, we have different things. The grass here is going to act on the soccer ball, and the soccer ball is just going to sit there until it was kicked. A force was applied to it, right? Um, so that's what's going to happen with X-rays. And we're going to see that as we continue to talk about physics in X-rays. So that's kind of why that's brought up. There's also a little video there if you want to take a look, and we will in class. All right, so again, a photon is going to keep moving unless it hits something else like atoms. So that's one of the reasons we have a vacuum. This is our vacuum tube right here, right? If this were not a vacuum, there would be atoms floating all through here. Of course, we can't see them. They're just in the air, oxygen, hydrogen, things like that. They'd be floating around in here. And every time we tried to produce X-rays, those electrons that come off the cathode here would interact with those atoms in the air, and the whole process would be really inefficient. By removing anything and everything that could be in this space, except for the physical components, basically removing the atoms in the air, we create a vacuum. So those electrons, nothing's going to happen until they reach that anode. Like the anode is where they're going to interact with something and make X-rays for us. So that's one of the reasons for the vacuum in there. It's all based around physics. It will reach the anode in that vacuum. All right, so energy is the ability to do work and exists in two states. We're going to work a lot with potential and kinetic energy. So potential energy is energy in a storage state. So maybe think about a storage unit, something like that, and you have all this potential sitting there, right? Just kind of like humans, right? We have so much potential. But It's what we do with it that matters. So that's when we have our kinetic energy. So we're going to open up those boxes, open up that potential. And as soon as things start happening, we have our kinetic energy. I put in this kind of gray scene here, which actually I kind of like. But anyway, the gray is the SI unit for absorbed dose, right? So just continuing to talk about units of measure. And remember, when we're talking about radiologic units, which again, is going to be more of a focus in like patient care and safety, um, we're talking about special units, right? So the gray, you see kind of a gray day here, is a measure of the amount of radiation absorbed by tissues. So we can say, oh, it's such a gray day. I'm not going to get any sunlight. I'm not going to absorb any sunlight. But gray is talking about how much radiation we're getting. Okay, so another unit, for example, a special unit is a sievert. So a sievert is used to quantify occupational dose. That's important for us. So if we think about Dr. Sievert and their occupation here, we can maybe remember that, that's the occupational dose. And then KERMA, that's another one we'll use in physics too, but it's an acronym for kinetic energy, right? That something's happening, released per unit of mass. And it's an expression of energy released per unit mass. So I thought of Kerma, like kernel, popcorn kernel, and how much energy, this is kinetic energy happening right here. Things are happening. So it's just kinetic energy released per unit of mass. Finally, radiographic equipment. This should look familiar. We, in this course, are actually going to learn all about what each of these buttons basically are doing, what each of these are doing, but inside the actual X-ray circuit. So KVP and MA, those are going to be our energy, right? We have a fundamental quantity here in seconds, and then we have other things going on as well that we're going to learn all about.